All right, y'all, here's my solution to the Colonel Armstrong problem. Recall that it's related to the redwood tree whose trunk is 300 feet tall. Every 60 feet, a diameter measurement was taken, and they showed a picture of it that looks something like this. So at the very base, there was a diameter of 14 feet. And then 60 feet up, the diameter is now 12 feet. Another 60 feet up, the diameter is now 10 feet. Another 60 feet, 9 feet diameter, 8 feet diameter, and at the top, another 8-foot diameter. And the question was to find the volume of the trunk of this tree. That's my tree. Looks more like a palm tree, doesn't it? Hey, what we're going to do is slice this up into infinitely many, infinitesimally thin slices. Now, a slice of this tree trunk, if I could just draw it in here, looks like a cylinder. And the volume of a cylinder is found by taking the area of its base, pi r squared, and multiplying it times the height. So can you imagine finding the volume of each and every one of the infinitely many? Now, I know there's 1, 2, 3, 4, 5, 6 shown here, 6 kind of cross sections shown, but we're going to imagine not just 6, but infinitely many of them. The issue is the radius of these cylindrical slices changes. For instance, the radius down here at the bottom, with a diameter of 14, the radius would be 7. The radius would be 6. The radius would be 5. The radius would be 4.5, 4, 4. So depending on how high up into the tree we are, we get different radii. And so kind of like the dam problem, you'll notice that the radius of the cylindrical slice depends on the height. Now, when the height is 0, so come on back here to 0, the radius is 7. Remember, the diameter was 14. Whoops. Hey, I have an eraser. The radius is 7. So we could maybe make that little note. When height is 0, radius is 7. Now, the way it was worded, let me just read it again to get it, make sure I say it right. Every 60 feet, a diameter measurement has been taken. So this is 60 feet up. So if we went up 60 feet, we're going to get a diameter of 12, therefore a radius of 6. So when height is 60, radius is 6. And then another 60 feet, that would be 120. We get to this one, the radius would be 5. So imagine here 60, 120, 180, 240, 300. We now have a radius of 5, so 7, 6, 5. Sounds linear to me. Let's keep going. When the height is 180, that would get me to this one. Now the radius is 4.5. That kind of breaks my nice linear trend. When the height is 240, the radius is 4. I'm talking about this 8-foot diameter up here. So a radius of 4. And again, at the top, when the height is 300, the radius once again is 4. So we go to 4.5, 4, 4. So a linear function is not the most perfect way to address this. I'm going to encourage you to jump on Desmos and see if you could take this data and put it in a scatter plot and try to see what kind of a function best models that. Now I'm going to jump over there too, but I would encourage you to pause and play with Desmos for a minute. What kind of a model for the radius of the cylindrical slice we're speaking of, which depends on the height, based on the data, could we come up with a function formula that would describe the radius for any height? Will you please pause and go play with Desmos for a minute? And when you're ready, come on back. So I went on to Desmos, I hope you did too, and I found that the radius as a function of height is given by this quadratic. This nice quadratic function best models the data. Let me just show you quickly what I did. So first of all, if you hit the plus sign, you can add an item. I added a table, and I just typed in our case, x represents the height above the ground from 0 to the 300 feet. And y represents the radius of that cylindrical slice of tree trunk from 7 down to 4. And then to have Desmos give you a function that would model the data set, you type y sub 1. And by the way, just literally hit the y, hit the 1. Desmos knows that you probably want a subscript. So y sub 1, and then the tilde, find the tilde on your keyboard. And then I typed in the general quadratic format. So a coefficient of a times x squared, a coefficient of b times x, plus a constant c. Again, notice x sub 1 because the data up here is x sub 1. And as soon as I hit enter from that, I get my parameters. The coefficient a is 0.0000, etc. The coefficient b, the coefficient c. I don't know if you know about r squared, but an r squared close to 1 means you have a pretty good fit for this quadratic on this data set. So we have a pretty good fit. So there it is. Let's go back now and get to work on the real stuff. The real stuff here is the volume of one of these slices is found by taking pi times the radius. Oh, but the radius changes. But how does the radius change? Haha, now we know. The radius changes depending on the height. So what we're now going to say is the volume of a slice is going to be pi times the radius, which is this function down here, squared, times the height. Now imagine like this particular disc I was talking about, this cylindrical disc of wood, has a height there of infinitesimally thin. Because if I make it infinitesimally thin, then the radius for that slice will be the 6, or the 5, or the 4, or the 4.5, or the 7, or whatever it was. So if I make my slice infinitesimally thin, a little change in h, and if I sum up that stuff, what stuff? Exactly. The stuff I'm summing up is the volumes of all infinitely many of those cylindrical chunks of tree trunk. And the volume of each of those chunks is pi times the radius, which changes according to this thing over here, squared, times the height, which is that little infinitesimal dh. And if I sum up all of those from the bottom, height of 0, to the top, height of 300, I will get the volume of the tree trunk. Now I encourage you, in this case, I am not going to integrate by hand. I just don't feel like it. To be honest, it's late at night right now, and I'm just going to use Desmos to integrate this one. So here we go. I think on this I can say f, let me pause here for a minute. I paused to make sure I could do this, but yeah, if I type in f of x equals ax squared plus bx plus c, Desmos will draw on this previously determined values for a, b, and c. So notice here in red, the function certainly is in red. Let me turn it off. Oops, let me turn it off. Turn it back on. Yeah, look at that. So now what I can do is say, hey Desmos, integrate integrate from 0 to 300. And what I'd like you to integrate is pi times the radius squared, where the radius is that function f of x. So there's pi r squared, and the height is the dh I was using on paper, but we're now going to call it dx for the sake of Desmos. And bammo, 24,158. Let's call it 24,158. So the volume of this tree trunk is 24,158 cubic feet of volume. Nice. I hope you got the same result I did. If not, figure out who's wrong, me or you. I don't know. It could be me. Find my mistake. Do it.